Would you rather dive into the sea from a cliff or wade in slowly from the shore? For me, it's the shore every time. I like to avoid risky situations. Interestingly, these two ways of entering the sea are just like chemical reactions. Some happen in one dramatic leap, while others ease in gradually and can even go back and forth. This is Real Chem. Understanding the nature of dynamic equilibrium in chemical reactions is a big deal. The reactants and products are dynamic. They're constantly moving. When I was a student, I found these principles confusing until I learned to think of them like people at the beach. Some things in life are easy to reverse, while others are not. Think about jumping into the water from a cliff. For some, that might be easy. A brave person could leap into the water effortlessly. But jumping back onto the cliff, that's impossible. This illustrates an irreversible process. You can't follow the same path from the water back to the cliff. Now imagine walking into the water at the beach. This is reversible. Walking from the water and back onto the beach is easy. The same principle applies to chemistry. Some reactions, like the combustion of hydrogen with oxygen to produce water, only proceed in one direction. They are not reversible. On the other hand, reactions like this one, where azobenzene changes geometry when exposed to heat or light, are reversible. Upon light exposure, trans-azobenzene transforms into its cis isomer. Cis-azobenzene can also revert back to its trans form upon irradiation by light. For reactions that only move forward, we assume that they go to completion, meaning that the reactants convert to the products until one or more of the reactants run out. To predict how much product is formed, we use the concept called limiting reagents. For reversible reactions, we need a different set of tools, which fall under what we call chemical equilibrium. Let's revisit our beach example. On a hot day, we might notice that the ratio of people on the beach to those in the water is 3:1. Later in the day, the ratio is still 3:1. However, it's not the same people in the water. Some people have gone in and others have come out. The number of people in the water didn't change because, on average, for every person who went into the water, another person got out. We can say that the rate of the process in one direction is equal to the rate of the process in the other direction. This is what we call dynamic equilibrium. The ratio between the number of people in the water and the number on the beach stays constant, meaning we've reached equilibrium. But both processes are still happening, so the equilibrium is dynamic. The same is true for molecules. In a chemical system, we might observe that the ratio of trans-azobenzene and cis-azobenzene remains 3:1. But that doesn't mean that the forward reaction and the reverse reaction have stopped. It only means that the rate of the forward and reverse reactions are equal, keeping the ratio of trans-azobenzene and cis-azobenzene steady. This is what we mean by dynamic equilibrium. Whichever way you choose to get into the sea, jumping from the cliff or walking from the beach, doesn't make much difference. But don't forget, one of them is easily reversible, the other isn't.